we hear as a function of frequency. Different pitches correspond to different frequencies. Different notes in music correspond to different frequencies. And our inner ear analyzes things by frequency. So it makes sense that we would want to look at random signals and get a sense for what frequencies are present within these random signals. We're going to start by restricting our analysis to stationary random signals. When something changes in its characteristics over time, it's harder to talk about frequency. Traditional Fourier analysis uses trigonometric functions, sines and cosines, and these are signals, are basis functions that are infinite in length. When we start looking at windowed analysis, we get something different, but we'll start right now with stationary random signals. When I was young, a friend of our family's was an orchestra director, and I one time was driving him someplace in the car, in my truck actually. I had big mud tires on it, and these tires of course made a lot of noise as we drove. He uncharacteristically asked me to speed up. It's not like him. I asked him the reason, and he said that the tires were producing a note that was just a little bit flat from a G, and that if I sped up a little bit it should hit a G right on, because being just a little bit off pitch was really bothering him. Well, we can talk about the frequency of random signals, but I want to first introduce a problem that we have to overcome, and that is that we cannot take the Fourier transform of an infinite length sequence. So why does this even come up? It comes up because if a random signal is stationary, that means its statistics never change for all time, and therefore it must be an infinite length sequence. We're going to restrict also our discussion right now to discrete time sequences, and the Fourier transform of a discrete time sequence x would be the sum over all time minus infinity to infinity x of n e raised to the minus j, the imaginary number, omega n. Well, for starters, the magnitude of this is 1. And so if we look at this sum, x never dies away. It always has the same magnitude, whatever that might be. Not magnitude, expected variance or energy or power within that signal for all time. Therefore, this sum won't converge. So, instead, we're going to compute the Fourier transform of the autocorrelation function, and this is something that we will call the power spectrum. So this quantity, actually, we'll find it makes a lot of sense to talk about the power spectral density, but one of the functions, or the properties rather, of the autocorrelation function is that it tapers off. It dies off unless we have a truly deterministic periodic function for any random process. The power spectral density has finite energy. And so in this case, finding the Fourier transform of the, or DTFT, discrete time Fourier transform of the autocorrelation function yields a quantity that we can understand. So here's the power spectral density. It's a function of frequency, and following the notation used in the several textbooks, such as Oppenheim and Schaefer's discrete time signal processing, we use the argument e raised to the j omega to indicate that this is a frequency domain quantity of a discrete time or sampled process. So let's see why this is such a good fit. Suppose that we had a signal x of n that whose Fourier transform actually exists, where x e to the j omega is equal to the dt ft of x of n. So this x of n, of course, then cannot be a stationary random process, but let's just say it's some signal for which the Fourier transform exists. How do we get the autocorrelation of that signal? Well, our estimate of the autocorrelation function of this signal is going to be found as the sum from k equals, I'm going to put in infinite, let me just leave off the whatever the appropriate limits on the summation are, x of n, x, that should be a k, x of k, x of k plus m conjugate, and divided by the length. So we've got this. Well, what happens if we take the Fourier transform of that? Let's start by writing this in another way. This is equal to 1 over L times x of k involved with x of minus k. Remember, convolution is going to have, just as an aside here, so you have it handy, it's the sum of x of n minus k. Note, as I was writing that, I realized I'd made a mistake here. I should have had m in the arguments to match that one, so I fixed it. If you were taking notes and missed that, you can go back and make the change. Okay, so if we take the dtft then of our estimated autocorrelation function, that's going to be the dtft of 1 over L times x of m times x star, or conjugate of minus m. And this is actually quite easy to prove, but we won't do it right now. If you doubt it, prove it yourself or go look in a Fourier transform table. Doing the conjugate time reversal is going to give us this, which is just the magnitude of e j omega squared. So what is this telling us? The Fourier transform of our estimated autocorrelation function actually looks like the Fourier transform of our signal magnitude squared? Well, when we find the magnitude squared of a spectrum, we're looking at the power spectrum. So the power spectral density makes a lot of sense then as a Fourier transform of our autocorrelation function. Okay, let's look at a specific example, one that's very important to know because it's used a lot. And that is the idea of white noise. For white noise, every sample is uncorrelated with every other sample. So that means that we have our autocorrelation function. This is once again a stationary signal, is equal to the variance times a delta function. This is the Kronecker delta, and delta of m when it's discrete, when the argument is discrete, is 1 for m equals 0 and 0 everywhere else. In other words, none of the samples are correlated with each other. The autocorrelation function is 0 everywhere except the one place. The Fourier transform of a delta function is just its argument. In other words, the power spectral density is constant over frequency in all frequencies. Hence the name white noise, because white light has all colors, and this signal, or a white noise signal, has all frequencies present.